Good morning, my dear friends. I hope you all are doing great. Dear friends, today we have come up with a topic which is relation between equilibrium constant, reaction coefficient and Gibbs energy, my dear friends. So let us see first of all the mathematical expression of thermodynamic view of equilibrium. So obviously in the thermodynamics chapter, I have given you idea about one mathematical expression which was like this. Delta G is equal to delta G naught plus RT ln QC. There in thermodynamics, I have written here Kc. Yes, QC can be equal to Kc when the reaction is at equilibrium, my dear friends. So let me call it as equation number 1. This is our change in Gibbs free energy. So this is change in Gibbs free energy. And this one is standard change in Gibbs free energy. Standard change in Gibbs free energy. R is our ideal gas constant. T is the temperature in Kelvin. Temperature in Kelvin. Ln is the natural log. It is a natural log. Okay. And QC is the reaction coefficient, my dear friends. In previous classes, we have read actually about reaction coefficient. When we were discussing about like predicting the direction of the reaction, we have given the relationship 3 cases. QC greater than Kc, QC equal to Kc, QC less than Kc, while predicting the direction of a chemical reaction, whether it will move in forward direction, backward direction, or both forward and backward together. So my dear friends, after learning this particular thing, let us go further and let's take on one chemical reaction. Let's take on A plus B gives C plus D. This chemical reaction is at equilibrium. So these are stoichiometric coefficients, my dear friends. So I will write down at equilibrium, we have one thing here. Remember always, I have told you many times, equilibrium will take place in a closed system at constant temperature, correct? So obviously let us take on here, at equilibrium, delta G is equal to 0. Change in Gibbs free energy is 0, but not standard change. Just change in Gibbs free energy, which is delta G is 0, my dear friends. And simultaneously, while predicting the direction of reaction, there also I told you that QC is equal to Kc. Reaction coefficient is equal to equilibrium constant at equilibrium. That means QC is equal to Kc. In place of this QC, you can write down Q also. But C stands for in terms of molar concentration I am writing here. So these two terms are equal. So we know at equilibrium these are actually the values of for delta G is 0, QC is equal to Kc. Let us put these values of delta G and QC in equation number 1. Okay? Put values of delta G and QC in equation 1 we get. So what we are going to get, have a look, my dear friends. Can you please focus right up here? So look here, my dear friends, I will put these values in that equation. We know that delta G is equal to 0. Delta G is 0. So this term will become 0. This delta G will become 0. Okay? So obviously we will have 0 here. Delta G naught is not 0. Okay? Only delta G is 0. Change in Gibbs free energy. This one. Now what about this QC? QC will become equal to Kc. That is equilibrium constant. Reaction coefficient will become equal to equilibrium constant at equilibrium. Correct? My dear friends. So in place of this QC, I will write down Kc. So I will have plus RT ln is a natural log. So now in place of QC, my dear friends, I will be adding on Kc. So I will add on Kc. Correct? So let us transfer the values. Let's take on this particular term, delta G naught, to this side. So I will get here minus delta G naught is equal to RT ln Kc, my dear friends. So this is my expression. So after getting this expression, let us call it as equation number 2, my dear friends. So minus delta G naught is equal to RT ln Kc. Now you will be thinking, what is this ln all about? I have already discussed with you in the first part of this chapter, chemical equilibrium, that log and anti-log values, they will be applicable here also, my dear friends. So have a look. This is a natural log, my dear friends, ln. So for you people, I will write down once again. What is ln equal to? At natural log, it's equal to log to the base e. So natural log is equal to log to the base e, and it's also equal to, if I transfer it into common logarithm, this is natural log. If I transfer it to common logarithm, what is that? 2.303 log to the base 10. Now my dear friends, in place of this ln, it's your choice. Either you want to mention this ln, a natural log, by log to the base e, or you can mention this ln, this natural log, you can mention it as 2.303 log to the base 10. Let me take on this value, my dear friends, this expression, and later if it's your choice, you can use this expression also, it's up to you. So let me use this one. And we should also mention that this ln is which log, my dear friends? I have already told you, this is a natural log. And simultaneously this e is a base here. So this e is called as Euler's base. And this Euler's base is equal to 2.7. So let's mention it as 2.7. Okay? And what is the base for this? This is common logarithm with a base 10. Correct? So how is natural log related to the common logarithm with a base 10? That natural log is equal to log to the base e is equal to 2.303 log to the base 10. Now in place of this ln, my dear friends, let me use the value log to the base e. So this expression I will use here. Okay? So my dear friends, let us write down now minus delta G naught. Okay? So look here guys, I will be changing this expression to this expression, my dear friends. ln I will write down log to the base e. So it's equal to RT, in place of ln, I can write down log to the base e, or I can also write down 2.303 log to the base 10. So it's our choice. Let us mention this one. So I'll mention here log to the base e, then Kc. Okay? So this is my expression right out here, my dear friends. Now after this, okay, I can further simplify it. Okay? Let us call it as now equation number 3. So please make note of this, and I will simplify then equation number 3. Dear friends, you have learned minus delta G naught is equal to RT log Kc, correct? And the base is E, that is Euler's base, my dear friends. Now let us further simplify this expression. Let's take on our expression minus delta G naught is equal to RT log to the base E Kc, correct? This is our equation number 3, correct? So let us further simplify it. Let us keep this log to the base e, okay, right out here on this side, and let's transfer RT to this side. So I will get here log Kc to the base e here, okay, is equal to minus delta G naught divided by RT. So this is my expression, my dear friends. So what I am going to do after this, please try to understand. Let's call it as equation number 4. I have already told you one thing, if you remember, okay? What I have done here, my dear friends, I want to tell you. RT you take down, it will become minus delta G naught RT. Take this RT down. So I wrote the same, minus delta G naught divided by RT. And this log Kc will remain there. So log Kc remains there, okay? So what I am going to do, try to understand. I have told you already this in the first part. That was, if you have a log, and log can have a base 10 also, log can have a base e also. Here we have a log with base e. So let's suppose I have a log with base e. And here I have x. I want to find out log x. What is the base here? E. Is equal to, let us suppose, y. So how can I write down? If log x is equal to y. Okay? How can we written it? Then, try to understand. Then, take the base. What is the base here? E. Just a minute, my dear friends. So e to the power y will be equal to x. So e to the power y will be equal to x. So take the base e, take y as a power, and it will be equal to x. So e to the power y is equal to x. So this thing also we have to do here. This is your e. This is e. This is your y. And then this kc is your x, my dear friends. So e to the power y is equal to x. Like here, e to the power y is equal to x. So same thing, e to the power y. What is y? Minus delta G naught RT is your y. Correct? And it's equal to x. And what is x? Kc is your x. So Kc is your x, my dear friends. So let us see here. So let us use this expression, my dear friends. So what should I use here? E to the power minus, so I will write down the e to the power minus delta G naught by RT, correct, is equal to x. What is your x? Kc. So it's equal to Kc. I hope you have understood, my dear friends, this particular expression. So now, my dear friends, we can have the situations here like this. How we can relate it to the spontaneity or non-spontaneity of a chemical reaction, we will look into it, my dear friends. Please make note up to it. Dear friends, you have gotten the expression now e to the power minus delta G naught upon RT is equal to Kc. So now Kc is equal to e to the power minus delta G naught upon RT. Let's call it as equation number 5. Okay, so this is equation number 5, my dear friends. Now what is the use of this equation? Let us see. We can understand, my dear friends, remember, we can understand spontaneity and non-spontaneity of a chemical reaction through this particular expression. And you should also remember this E. E stands for Euler's base. I have already written the value of this. This is 2.7. Euler's base, correct? So let us go further. Understand it. If delta G naught, I am talking about this delta G naught. If delta G naught is less than 0 or negative, let us suppose if this value is negative, my dear friends, have a look. This delta G naught, less than 0 means negative. So have a look here. If this guy is negative, then minus into minus will become what? Positive. Yes or no, my dear friends? If delta G naught is less than 0 means negative, then negative into negative, because in place of delta G I will write down minus. The minus into minus is plus. Yes or no, my dear friends? So try to understand. Correct? So if delta G naught is less than 0, then this expression I am talking about, this entire expression, then minus delta G naught upon RT is positive. Now somebody may think that how it is positive. I just told you right now, if delta G naught is less than 0, that is negative. So in place of this delta G naught, what I have to write down? Negative. Then negative into negative will become what? Positive. So this entire expression will become positive, my dear friends. Correct? So we have a positive expression. So once again, if delta G naught is less than 0, then minus delta G naught upon RT is positive. Okay? Which means, let's write down the entire expression now. Which means e to the power minus delta G naught upon RT. When minus delta G naught by RT is positive, then at that time e to the power minus delta G naught by RT is greater than 1. Remember, because E is 2.7, E is 2.7, Euler's base, and minus delta G naught by RT is positive value. So 2.7 having any positive power will be obviously greater than 1. So when it's greater than 1, okay, which means e to the power minus delta G naught by RT is greater than 1. And Kc, thus Kc will be also greater than 1. We can write down, thus Kc is greater than 1. When this expression e to the power minus delta G naught by RT is greater than 1, that means Kc is also greater than 1. Okay, so what will happen? Look here, if delta G naught is less than 0, that is negative, then minus delta G naught by RT. I'll put here this minus value for this delta G naught by RT, minus into minus is plus, so it will become positive. Which means e to the power minus delta G naught by RT. This entire value, I have already told you, this entire value is basically positive. So when this entire value is positive, e has a value of 2.7. 2.7 having a power which is positive will be greater than 1. When it's greater than 1, when this entire expression is greater than 1, Kc will be also greater than 1. So when Kc is greater than 1, okay, remember. So now my point will come, when Kc is greater than 1, okay, the reaction is spontaneous, okay, which means forward reaction will take place and the molar concentration of products will be far greater than the molar concentration of reactants, my dear friends. So remember this important point. When Kc value is greater than 1, the reaction is spontaneous, which means forward reaction will take place. That means reactants will change into products easily because it is spontaneous. Reactants will keep on changing into products. So reactants will keep on decreasing and products will keep on increasing. So the molar concentration of products will be far greater than the molar concentration of reactants, my dear friends. Please make note of this. And after this, we will take on the case number 2. Okay. So case number 2 will be, opposite of this particular thing. Please make note. So dear friends, let us take on now case number 2. In case number 1, we have taken delta G naught less than 0. So in case number 2, try to focus here, sir. Case number 2, we will take on delta G naught greater than 0. Greater than 0 means positive. Okay. So if delta G naught is greater than 0, then look at this expression. Minus delta G naught upon RT. And here we know that this delta G naught is greater than 0, that is positive. So this entire expression is positive. So positive into negative is what? Plus into minus is what? Minus only. So that means then minus delta G naught by RT is negative. So when this is negative, then what will happen to this expression? Which means e to the power minus delta G naught by RT. You know the value of e. E is equal to 2.7 Euler's base. So 2.7 will have which power now? Because this entire expression is negative now. Because positive into negative is negative only. So this expression is negative. So e will have a negative power. So when e has a negative power, here it was having, e was having a positive power. Because this expression was, here it was negative. Negative into negative is what? Positive. Because delta G naught is less than 0, that is negative. So negative is positive. So you have a positive expression. E has a positive power. When E has a positive power, that means 2.7 has a positive power. When 2.7 has a positive power, it will be greater than 1. Then Kc will be also greater than 1. Now look here, which means e to the power minus delta G naught by RT. Plus into minus is what? Minus. So E has a negative power. 2.7 has a negative power. What is the meaning? Thus, okay. If it has a negative power, first of all we will write down, but it will be equal to 1 or less than 1. Which means e to the power minus delta G naught by RT is less than 1. Okay. Thus, when this entire expression is less than 1, thus Kc is also less than 1. So when Kc is less than 1, so we'll write down here, when Kc is less than 1, okay, the reaction was spontaneous there, but here the reaction is non-spontaneous. The reaction is non-spontaneous. In forward direction. So in forward direction, reaction is non-spontaneous. So when reaction is non-spontaneous, how much of reactant will change into product? A small amount, very small amount of reactant can change into product. Because reactant does not want to change into product. Because reaction is non-spontaneous, and non-spontaneous reaction requires lots of energy, lots of temperature. So obviously here, the reaction is non-spontaneous in forward direction. Or in simple words also, small amount, very small amount of reactant can change into product. So here, In this case, let's mention here one note, very small amount of reactants change into product. Why very small amount of reactants are changing into product? Because reaction is non-spontaneous, so little amount, very little amount of reactant will change into product. But here, large amount of reactant will change into products, and products will become greater than reactants. Here reactants are decreasing and products are increasing. So products are greater than reactants. But it's a non-spontaneous reaction, so only little amount of reactant will change into product. Very small amount of reactant. Yes? We can also tell negligible amount of reactant will change into product. So when reactants are not ready to change into product, then understand who is dominating here. In this case, who will dominate? Understand, in this case, reactants will be far greater than the products, my dear friends. Why? Because only a very small amount of reactant is changing into product. But if you want more and more reactant should change into product, then you have to give more temperature. Why you have to give more temperature? Because the reaction is non-spontaneous. So let us mention here, it's a non-spontaneous reaction, my dear friends. I hope you have understood these two cases and all. Okay? So please make note of this. Dear students, now let us have a look at Le Chatelier's principle, my dear friends. It states that any change in temperature, okay, pressure, concentration imposed on the system at equilibrium, means if your system is at equilibrium, means any chemical reaction or physical process has attained equilibrium, okay, is present at equilibrium, and you are forcing some change on it. What kind of change you are forcing on the process at equilibrium? You are forcing the change in temperature, change in pressure and change in concentration on a system which is at equilibrium. You remember one point, that at equilibrium the temperature is basically constant. So if you change the temperature, that means you will be disturbing the equilibrium, my dear friends. So what you are forcing onto the chemical reaction which is at equilibrium, you are forcing the change in temperature. That's what you are doing. You are changing the temperature. That means we are imposing the change on the system. We are changing the temperature. Equilibrium was at constant temperature and we are changing it. So we are imposing the change on the system. When we impose the change on the system, the equilibrium will be disturbed, my dear friends. Then what will happen? Once the equilibrium is disturbed, then have a look. Is opposed by the system. Whatever the change you are imposing on the system will always oppose it. What is the meaning of that? I will tell you. If you increase the temperature for a reaction at equilibrium, the system will decrease the temperature. So you are imposing increase in temperature and the chemical reaction will decrease the temperature. If you decrease the temperature from outside, the chemical reaction will increase the temperature. That means whatever you do for a reaction at equilibrium, the reaction will do opposite of that. Yes or no, my dear friends? If you increase the concentration of reactants, yes or no, the chemical reaction will decrease the concentration of reactants. If you increase the concentration of products, yes, if you put more products from outside into the system at equilibrium, then you are increasing the products and the chemical reaction will decrease the products. How to decrease the products? Products will change into reactants. Yes or no, my dear friends? So if you increase the pressure, the chemical reaction will decrease the pressure. So how is it happening? You have to understand it in this particular topic, that when you are imposing any change onto a system which is at equilibrium, that change will be opposed by the system. You increase the temperature, the system will decrease the temperature. You increase the concentration of reactants, system will decrease the concentration of reactants. Yes? You increase the pressure, the system will decrease the pressure, my dear friends. And how all these things are happening, we will understand them one by one, my dear friends. So now, my dear friends, if you are imposing some change on the system is opposing that change. Why does system oppose the change? That is also the question. Because system is opposing the change so that it will again come back to the equilibrium, because you are disturbing the equilibrium. Yes, you are imposing the change, you are disturbing the equilibrium, and the system is opposing the change, doing the opposite of that, and so that it will regain the equilibrium. Now let us understand that what are the factors which will affect the equilibrium or equilibrium. Have a look. Factors affecting the equilibrium, or you can say equilibrium. So what are those factors which we have to study? The first factor will be here, effect of temperature. Temperature will affect the equilibrium. Second factor is effect of pressure. Third factor will study effect of concentration. Fourth factor we study here, effect of addition of inert gas. And one more will study effect of catalyst. And there are many more factors. Let us study them one by one, my dear friends, and we will apply the Le-Chatelier's principle. So whatever the change you are imposing on the system at equilibrium, the system will oppose that change so that it will regain the equilibrium. Means it will regain the equilibrium, it will come back to the equilibrium. Yes or no, my dear friends? Please make note of this. Dear students, let us study now effect of temperature change over equilibrium state. Let us understand it, my friends. Let's take on one chemical reaction. N2 gaseous plus 3 times H2 gaseous gives me 2 times NH3 gaseous, my dear friends. So that is my chemical reaction, my dear friends. Okay. So what we are going to do is that we will look into it, that how does the temperature will affect it. Yes, because as far as Le-Chatelier's principle is concerned, any change, okay, imposed on the system at equilibrium is opposed by the system. So let us suppose this reaction is exothermic in the forward direction. That is, this is the value, my dear friends. So this reaction is exothermic in forward direction, my dear friends. When this reaction is exothermic in forward direction, then it will be endothermic in backward direction, my dear friends. So backwards we will be getting here delta H is equal to plus 92.38 kilojoules per mole. So this reaction is endothermic in backward direction. And look here, in forward direction, man, this is exothermic. This reaction is exothermic in forward direction. So now you are knowing that in forward direction, when reactant is changing into product, this is exothermic. Okay, so here the delta H will be negative, my dear friends. And in backward direction, my dear friends, this is endothermic. So delta H will be positive here, my dear friends. So what is the effect of change of temperature on the equilibrium, my dear friends? And you know that this reaction is at equilibrium. When this reaction is at equilibrium, then we are going to disturb that equilibrium. How? By changing the temperature. So let us see how we can disturb it. Have a look. So let us impose the change. So I will write down here change imposed. Okay. So for this chemical reaction, let me increase the temperature for this chemical reaction. We know that for this chemical reaction, the temperature will be constant. It will be taking place at constant temperature, at equilibrium. So what I am going to do, I am increasing the temperature for this chemical reaction. So it should do opposite of this. It should oppose the change. This is the change imposed, and it should oppose this particular change. I am increasing the temperature. The system should decrease the temperature. So change imposed on or over the system. Change imposed over the system at equilibrium. So this system is at equilibrium. I am imposing the change over it, that I am increasing the temperature. And remember these points here. Increase in temperature. Okay? Increase in temperature favors endothermic reaction, and decrease in temperature favors decrease in temperature favors exothermic reaction. So if you are, these are the chains imposed, my dear friends. These are the chains imposed over the system at equilibrium. So these are the chains imposed over the system at equilibrium. What happens if you increase the temperature for a system? The increase in temperature favors endothermic reaction. Very easy. And decrease in temperature favors exothermic reaction. If you look at this reaction, Haber's process, okay, reactant is changing into the product, and when reactant changes into the product, my dear friends, that is our exothermic reaction. Okay, so here exothermic reaction is basically the reactant changing into the product. Correct? And what is endothermic? Endothermic is a backward reaction, and backward reaction means here the reactant will be formed from the product. Yes or no? So here the products will be changing into the reactant. Or you can also show it like this, in a reverse order, like this. You can also show it like this. Product is changing back into the reactant. So this is backward reaction and this is forward reaction. Now what I am going to do, change imposed over the system at equilibrium. I am increasing the temperature. What should system do? The system is at equilibrium. System should oppose the change. Oppose the change means it should decrease the temperature. And in which process temperature is decreased, my dear friends? The temperature is decreased in endothermic process, my dear friends. Endothermic process will decrease the temperature. Yes, my dear friends, please have a look here. So I told you, when you are increasing the temperature, it favors the endothermic reaction. So which reaction will take place? So endothermic reaction takes place. Okay, this is the change opposed by the system. Okay, endothermic reaction takes place. Tell me which one is endothermic reaction, forward or backward? Backward is endothermic reaction. That means backward reaction takes place. Backward reaction will take place. And what happens in backward reaction, my dear friends? Products will change into reactants. So products will change into reactants till equilibrium is achieved once again. Equilibrium is regained. Okay? So till the equilibrium is regained, my dear friends. So which reaction will take place here on increasing the temperature? The endothermic reaction will take place, and that is backward, my dear friends. Now if we look at the another thing here, my dear friends. Let us decrease the temperature from outside. We are imposing the change. So let us decrease the temperature. This is the change imposed. So look here, when temperature is decreased, there is a change imposed. Temperature decrease. Decrease in temperature favors exothermic reaction. So exothermic reaction will be favored. So now temperature is decreased. Now this term will become now. So what is the change imposed over the system? Temperature is decreased. So exothermic reaction will take place. Exothermic reaction takes place. And tell me, what is the exothermic reaction? Backward is endothermic, forward is exothermic. That means forward reaction will take place here. So my dear friends, forward reaction takes place, which means reactants will change into products. Reactants will change into products, my dear friends, till equilibrium is regained. So now what will happen, my dear friends, when temperature is decreased from outside? You are imposing the change, you are decreasing the temperature, and decrease in temperature will favor which reaction? Exothermic. So what is exothermic reaction, my dear friends? In exothermic reaction, heat will be released. You are decreasing the temperature, correct? So exothermic reaction takes place. When exothermic reaction takes place, correct? What will happen? Heat energy will be released, energy will be released. So when energy is released, temperature will once again increase. You are decreasing the temperature, but exothermic reaction will increase the temperature. This is the change imposed by you from outside, and this is the change created by the system at equilibrium, my dear friends. If you increase the temperature, yes or no, the system should decrease the temperature. At that time, endothermic reaction will take place. Yes or no, heat energy will be absorbed. You are increasing temperature, but reaction is absorbing the heat by doing endothermic reaction, and the temperature will come down, my dear friends. So whatever you are doing, the chemical reaction will do exactly opposite of that. You are decreasing the temperature, but chemical reaction is which reaction? Exothermic. It will release the heat. When heat is released, temperature will once again increase, my dear friends. You decrease the temperature, exothermic will increase it. So change imposed, and this is the change opposed. If you increase the temperature, endothermic reaction will take place, heat will be absorbed. Temperature is increased and heat will be absorbed, temperature will decrease. So remember, my dear friends, when you increase temperature, endothermic reaction will take place, and when you decrease the temperature, exothermic reaction will take place, my dear friends. You take any example now, you should always understand, my dear friends, that what is the effect of temperature over the equilibrium state. Yes? So that is about this particular factor, that is effect of temperature change over equilibrium state. And remember also one more thing, A plus B gives me C. This is a combination reaction. So remember, most of the combination reactions are exothermic. So A plus B gives me C. Correct? So it's which reaction? Forward reaction is exothermic. Yes? But when we look at backward reaction, this C will break into A plus B. That is backward reaction. That means you have to break the NH3 into N2 and H2. So backward reaction is here which reaction? Decomposition reaction. So you are breaking C into A and B. That's why it requires energy. So it is endothermic, my dear friends. So remember, the combination reactions will be mostly exothermic. They will release the heat. But dissociation reactions will be what? Endothermic. They will absorb the heat, my dear friends. So A plus B will give me C. Energy will be released. And C will break into A plus B. Energy will be absorbed. So endothermic, my dear friends. So combination reactions are mostly exothermic, but decomposition reactions are endothermic in nature. Let me give you one more example after this. Please make note of this. Dear students, this reaction is at equilibrium. So let us disturb this equilibrium. How can we disturb it? Effect of temperature change. So we are going to disturb the equilibrium. So let's write down, let us disturb. Let us disturb the equilibrium by changing temperature. So So this is just for understanding, my dear friends. So let us disturb the equilibrium. Okay, let us play with it by changing the temperature, my dear friends. So let us see. This reaction is at equilibrium, correct? So you know that forward reaction is exothermic, minus is here. So it is exothermic. So I can write down two things now here. We have here forward reaction. Forward reaction. Yes, and our forward reaction is exothermic. Exothermic. Correct? When forward, remember always, when forward reaction is exothermic, obviously the backward reaction will be endothermic. Backward reaction will be endothermic. If forward reaction is endothermic, then backward reaction will be exothermic, no problem at all. Okay? So this is our reaction. What will happen in this forward reaction? Reactants will change into product, and in backward reaction, products will change into the reactant. This is how it is happening, my dear friends. So we want to have a look, what will be the change of, or what will be the effect of temperature over the equilibrium of this chemical reaction, my dear friends. So let's have a look. Let's write down change imposed. Let us increase the temperature, my dear friends. And remember, when temperature is increased, increase in temperature favors endothermic reaction. And tell me, which one is endothermic reaction? Backward or forward? So backward reaction here, yes, is the endothermic reaction. So change imposed is temperature is increased. So what will happen because of this? Okay, favors endothermic reaction. And what is endothermic reaction? Forward reaction or backward reaction? Backward reaction. Okay. So products will change into reactants. So product will change into the reactant. Reactant will not change into product. Correct? So after that, what will happen, my dear friends? Product will keep on changing into the reactant till equilibrium is regained. So I will write down product will keep on changing into reactants till equilibrium is re-established. We can say equilibrium is regained, or you can say re-established. So very simple. So that have endothermic reaction is your nothing but endothermic is here backward reaction. It's not necessary that endothermic reaction will be always backward reaction. In some of the reactions it can be, forward reaction also, endothermic can be forward also. But here it is, endothermic is backward reaction. It also means that which thing will change? It means that N2O4 will change into NO2, my dear friends. N2O4 will change into this. That means here product is changing into the reactant, my dear friends, in this case, when you are increasing the temperature. And when you decrease the temperature, opposite things will keep on happening, my dear friends. So let us change it here. Let us decrease the temperature. Everything will become reverse now. Reactants will change into products. That means this thing will also change now. That means NO2 2 times will change into N2O4. Backward reaction will not take place. Now forward reaction will take place. Forward reaction takes place. As you know that temperature is decreasing. Look here, when temperature is decreasing, decrease in temperature favors exothermic reaction. Which one is exothermic reaction? Exothermic reaction is forward reaction. So now it will favor the forward reaction will be favored. And in forward reaction, product will not change into reactant, reactant changes into the product. Okay? Then what will happen? Reactants will keep on changing into products. This is a reactant. Reactants will keep on changing into products. till equilibrium is regained or re-established, my dear friends. So I hope you have understood this particular process. If I take some general information as well, my dear friends, you should be able to do that particular thing very easily. I hope you have gotten the idea. Okay, please make note of this. So dear friends, you have learned that the increase in temperature favors endothermic reaction and decrease in temperature favors exothermic reaction. So whenever you are imposing a change on a system which is at equilibrium, that means if you are increasing the temperature, then understand endothermic reaction will take place. If you decrease the temperature for a system, then exothermic reaction will take place, correct? So with this information, you will be able to solve the problems in examination, my dear friends. So we will look into the effect of pressure, effect of concentration, addition of inert gases and effect of catalyst onto the equilibrium state of a chemical reaction or a physical process by tomorrow. Till that time, have a great time. Yo-yo.